from this section which was just finished. We didn't say you the task. Maria, excuse me. Will you put the text of the task on the free access? Yeah. Okay, thank you. So Maria will put it on the free access, but nevertheless, I just read out for you this task. They are quite simple, so you can just write down. So 3A.4. Where is it? Three 8.4, 1 and 2 tasks. One and two. Let me dictate them. The first task is determine the radial gradient of the angular velocity of rotation directly on the right boundaries at r equal 1 and r equals c. So you have to determine the radial gradient of both, exactly at both these boundaries, just quite simple task. Another task is a little bit more lengthy. Please write down if you like. Using the result from the previous problem, this problem which I told you, determine the viscous torque acting on the outer rigid boundary due to the transfer of angular momentum from the more rapidly rotating inner boundary. So it's quite a task for the understanding how it is working, and perhaps we can even account some sort of the diminishing of length of the day or something like that. And what external force torque must be, I just made the comment, don't write it down, but nevertheless Maria will provide you. So and another question in this task is what external torques must be applied to these boundaries to ensure that their angular velocity of rotation are constant. It's an interesting question and quite physical. And estimate these torques and the accompanying acceleration of the mantle for the Earth using the appropriate quantities from chapter 1. Okay, chapter 1, it's in chapter 1, the very first chapter, where some quantities of the velocity of the Earth's angular rotation and so on is appear. Also, you will require mass of the Earth and everything you can find in the net, which is it's some sort of the mixture of this basically classic mathematical problem and already physical real problem. So this is two tasks. And then now we proceed to the next chapter, chapter 3b. We intentionally named this chapter because this is a new chapter, just to finish properly our previous lectures. And so not to introduce a mess, we just named the one chapter which describes the geostrophic flow and all geostrophic things as chapter 3a. And now when we are in shear layer, more complicated, but maybe in this sense more interesting, at least from a mathematical point of view. So it's so we named the chapter 3. Okay, maybe we'll remove that because actually we already done that. chapter 3b. So it's about shear layer. Shear layer. More precisely, shear layers. Of course, there is a plenty of them near the tangent cylinder. As already told you, tangent cylinder is normally this tangent cylinder. Okay, as we already told, there is a discontinuity in this picture. And after this, to resolve this discontinuity, we need shear layers. And I also should change for another PowerPoint presentation. Please, a bit late. Wait. Okay, this is chapter 3b, manifestation. I don't understand it. Okay, it's right. Okay, let's start. Okay. So we start from the paragraph which names shear layer structure. Shear layer structure, you can write down if you like. 3b.1. 3b.1. Shear layer structure. This is the title of the paragraph. So in a viscous shear layer located on a tangent cylinder, it is necessary to take into account that all variables change sharply with the cylindrical radius s across the layer. Of course, they have to change very sharply. Therefore, to study this layer, the original Navier-Stokes equation, which we have in the previous section without any a and b, just 3, like the increasability equation also as well, which appears even earlier, must be written in a cylindrical coordinate system. So everything when we explore in this shear layer, because it's in cylindrical direction, of course we should expand everything in cylindrical coordinate. Okay, the highest S, this cylindrical radius is denoted by S, like here, for example. And so the highest S derivatives. Of course, we are paying special attention to the highest derivatives. More higher derivatives, more on more smaller volume we divided the expression to which we apply these derivatives. So if we have more order derivatives, then we have more contribution of this term, related term, because we effectively divide it on smaller number. You should understand that. So the highest S derivatives across the layer will dominate over all the derivatives, which will allow us to neglect many terms in the equation for the leading order. In this case, only the terms that ensure the fulfillment of all physically necessary regularities and requirements should be remained. As a result, so see the detailed problem which I just stated to you about the gradient of the velocity. So it's not accident that I mentioned to you this problem, but from this problem, when you have this gradient, we obtain a system of four-scalar equation for the shear layer. This actually applying this idea that we identify more higher derivatives. So we can skip some things which are not important and leave only the things that are not important. That's written here, but I repeat it with the comment how it was obtained. The first equation in this reduced system, which take into account shear layer structure and that we should apply mainly the term with derivatives against S, where S is the cylindrical coordinate. Of course, we start maybe from the most important term, which is relate the pressure in this direction. It's geostrophic part term. Then it's equal to the Ekman number. Ekman number comes from the viscosity. And why we use the Z direction? Just because on the Z direction there is no Coriolis force. So here there is no Coriolis force. Why we use this expression? We start from the simplest one. Why not to do so? So we have, and when we consider pressure, it's obviously in that direction look like that. Coriolis term is vanishing in that direction because there is no any component of the velocity in that direction for the Coriolis force. So eventually, and if we consider the Laplacian term which multiplied it by Ekman number for this Z coordinate of the equation, we should keep only second order derivatives of the velocity, of course in S squared, of course. We could vary to the good accuracy to avoid and to neglect or to remove whatever you like, all other terms. There are plenty of them, but we can remove all of them. So it becomes in some sense rather simple equation. So let's proceed to the cylindrical coordinate. If we proceed to the cylindrical coordinate, of course in the first instance we have dp by ds. It's necessary to stress that it's more important even than that one, because here we have derivatives in the cylindrical coordinate, which exactly across the shear area. So it's put very important this term to the very rather importance. And of course here the Coriolis force is playing sufficient role. And there is again some cross is working on the on the equation which is related to the cylindrical coordinate. We get azimuthal coordinate of the velocity, of the Coriolis velocity, because actually originally this Coriolis velocity comes from the vector product. And then we actually, it's quite justified if we balance, keeping the balance of this term with the ordinary term. Then, because here we have not ordinary term, but one term which is correspond to the cylindrical radius, then we can be sure that at least in this respect we can neglect against this, against this, but from this part. So eventually Stevenson had an idea that this relation is equal 0. So it looks strange, but nevertheless it justifies the point that if we take this S derivative, it effectively multiplied, divided by this thickness of the boundary layer, e to the 1/5. But from other point of view, this term, this complete term, is about of order 1, and this term is about of order 1 over delta, or inverse Ekman number in square root. So it's more than this viscous. So we should keep this relation. Then if we consider the other component, phi component, there is no such a trick for that. And for this phi component, we have almost no pressure because, as far as I told you, we have almost no dependence on phi, and the gradient of pressure, of course, there is if there is no dependence on phi, so it's also zero. So in the next equation, which is phi direction, in fact, we have that the pressure term is disappear, and we left only with Coriolis term, which is of course balanced by viscosity term. So you see that always we have sort of the more or less unusual balance. Maybe here we emit Coriolis force, here we emit viscous force, and here we emit pressure. Everywhere there is some omission, but nevertheless it's working because we are making the approximation. And so we first of all want to make the major approximation to understand how these things work. And the final equation, we have three equations which follow from the Navier-Stokes equation. Of course, there is a continuity equation or divergence-free equation, so we of course have to use it. And this divergence equation could be written under this condition, like dvs over ds. Of course, this is quite natural term because I already told you that the divergence is somehow sort of the symmetrical function. So in fact, we have for this divergence we have first of all this derivatives, and also because there is not so big change in the z direction. So in this case, we have the velocity which is straight from the shear layer. There is a shear layer, so it's very difficult to penetrate from the shear layer from one part to another part. But it's quite easy to go straight to the shear layer. So we can, in that direction, in the axis of rotation, the shear layer is sort of the layer. So parallel to the layer itself, it's quite easy hydrodynamically that the velocity is going. So that component of velocity is rather important, more important than other components, because in shear layer we have the physically allowed the movement which is in that direction. Of course, it's also possible to satisfy from the integral form. So we keep the Vz component over dz. Okay. And finally, it's also zero. So this, it is obvious that this system zero, we name it, number is like a zero system, 3b.0. So it's obvious that this system zero is much simpler than the original system from 3.0 and 2.10. So original system, of course, much more complicated. But at the same time, it is noticeably more complex than the system for the Ekman boundary layer considered in the three previous chapters. So actually, you see that the system, of course, much more simple than original Navier-Stokes equation and even this version of the Navier-Stokes equation. But nevertheless, it's not so simple. It's much more complicated. So most complex than the system for the Ekman boundary layer especially. You remember that for the Ekman boundary layer we derived quite complicated system, and we started from the simple autonomic equation, which is actually effectively one-dimensional, because the valuable dimensional change are only in radial direction, and if we're near the boundary layer. And from another point of view, the outside the boundary layer also only one dimension. It's the cylindrical radius. So in different, of course, in different part of the volume of the liquid core of the Earth, which we modeled, there is different representation. But anyway, effectively, we finally represented only via the one coordinate, as a radial coordinate near the boundary layer, as this cylindrical coordinate, which we outside the boundary layer, and then it's working. But here, I'm afraid that this trick is not working, because it's quite difficult to reduce it to the one coordinate. But maybe we'll reduce at least to the second two coordinate or something. Let us try. So let's consider the things which Stewardson noticed and follow to him. So it's moreover, in the formulation of the boundary condition is a very non-trivial things. You see that I didn't write down the boundary condition at the moment, because even it is quite tricky things. This is due to the fact that the region under consideration near the tangent cylindric has cylindrical boundary in the horizontal direction. So it's, is it solution here? Oh no. Okay, we can go to this picture just to explain. So I just show you sort of the final result, but nevertheless it will be maybe a good guide for us for the moment. So in the horizontal direction and boundary condition on various spherical surfaces must be satisfied. You see that this shear layer intersects different. Here there is structure of the shear layer, and it intersects spherical, equatorial, here not equatorial, and it's actually constitute many shear layers. How to find them? Let's follow this Stewardson. So near that it's very non-trivial. This is due to the fact that the region under consideration near the tangent cylinder has cylindrical boundaries in the horizontal direction. So there is cylindrical boundaries in horizontal direction, like that. So and boundary condition on various spherical surfaces must be satisfied vertically. Many authors have made a significant contribution to the detailed formulation of this boundary condition, which essentially determines the solution. As a result of qualitative analysis of those boundary conditions, first of all, we came to the conclusion that the shear layer is divided into three sub-shear layers. It's interesting message. Here you see the final result, but nevertheless, people who explore that stuff found that it's divided on three boundary layers. Moreover, in the main sub-layer symmetrical located directly on the tangent cylinder, all members of the system of equation 0 are completely balanced. So with this complicated system is working only in the main part of the boundary condition, which is inside part of the shear layer. And here all the terms are perfectly balanced and completely. The system of equation 0, this system, after trivial identical transformation is reduced to the following two. First, equation for the vertical component of velocity. So let's do some identical transformation which Stewardson did. Okay, we have this zero system. Let's make some transformation to this system and explain every step of this transformation. Okay, we have that dp by dz, the first equation. We keep it like here. We keep it completely. Then we used some equation and reaching the result which put the pressure somehow outside. ds in force. That is equal dvz dz over dz. And then after definition of all these three stuff, which could be independently done, we have direct expression for the remaining two components of the velocity. V phi and Vs, cylindrical and azimuthal component. So all this stuff is coming out the identical transformation. So this is sort of the result which allow, anyhow, it's allowed to reduce for initial equation just to 2. And further we will proceed. In order to estimate the thickness of the main shear sublayer or its derivatives, we should make such a contribution. We should estimate somehow derivatives or in the cylindrical radius, because cylindrical radius for us is the most important. So we should estimate the derivatives in the cylindrical radius via the Ekman number. So we suppose that it's proportional to some power of the Ekman number. Of course, inverse Ekman number. For example, in Ekman boundary, this beta is 1/2. But for the shear layer, we suppose that there is some. So let's just estimate it. And of course, we involve the equation to do that. So from the first two equation of 1, you see that there is a derivative with respect to cylindrical radius that effectively work like this. And also there is some values of the which appears here. But anyhow, from the first two equations, we will assume that the pressure is related to the vertical velocity in order of magnitude. So these first two equations, which are only important here, this is just consequences. So we reduce the system, as I told you, just to two equations. So, and in these two equations, we could have only two variables. One is component z of the velocity, and another is pressure. So nevertheless, should be some relation between them. If we relate everything in the terms of the Ekman number, some power of Ekman number. So of course, for these two quantities, pressure and vertical component of velocity, of course, should be some relation as well. So we just suppose, quite reasonably, that the pressure, oh, maybe better to say it like that, that the pressure is proportional. Of course, it's not equal, it's just proportional in order of magnitude. So it's some power of Ekman number. E alpha Vz. Okay, we relate these two. So we have alpha and beta coefficient, and now we apply the condition that this equation match both sides, and this equation match both sides. Quite simple trick. And so here alpha and beta are the positive coefficients that must be found by balancing the leading terms in one in this equation. The order of magnitude for the term on the left-hand side of the first equation, this one. On the left-hand side of the first equation in one is e to the r, this one. E to the r. Because of this relation. And the term of on the right hand side is equal in order of magnitude, this term. Okay, let me show it somewhere here. Eventually it will be e to the 1 minus 2 beta. You can just make sure by yourself. Two beta comes from here. E to the 1 comes from here. So it's quite clear. It's 1 minus 2 beta, and this is equal I. So we get very simple relation from that. It's the consequences of this first two equations and this relation. So, and for them, so we balance it left hand side and right hand side. Since these terms must be completely balanced, we obtain the first equation for determining alpha and beta. So we have alpha equal 1 minus 2 beta. Very simple relation. Okay, second equation. Of course we balance it, these two terms. Now we can balance these two terms. And it's quite simple. But let me skip this step that you understand how we balance these two systems. I will just write down your result, but your task will be to do it by yourself, how to reach it. I hope that you could do. So the second equation look like that. 1 plus alpha minus 4b equals 0. Equals 0. So it's a linear system, quite simple linear system. Of course, it has a solution. Is obtained. So the solution of these two linear equations is quite simple, maybe even tremendously simple. Of course, we by intention we chose this coefficient alpha and beta in the way to have the simplest representation. So actually, this alpha is 1/3, and beta is also 1/3. So we have this rule if in Ekman layer the crucial things for us was square root from Ekman number, here in the shear layer, in the very nest of the shear layer, if you like, because it consists of from 3 shear layers, but the central one, which is the most important, of course, has the scaling like e to the 1/3. So its characteristic size working like that. Thus, the thickness of the main sublayer is a value of order e to the 1/3, as I said. In this case, as follows from the pennulative equation of system 1, this equation, the order of magnitude of the azimuthal and axial velocity is the same. Okay, so it also follows from this. Comparing to this velocity the pressure P and the velocity along the cylindrical radius S have a comparatively small relative value of the order e to the 1/3. You see that here the pressure is in these terms much smaller than component of the velocity, because Ekman is in positive power is expanding here. So in some sense pressure is smaller, in some places of course could be negligible. Accordingly, the solution of the first two equations from 1, again I stress we reduce initial system 0 from 4 equation and for 4 function as well, just to the 2 equation. And so actually, so the solution of the first 2 equations can be thought in the form. Actually, if we have pressure and z component of velocity, we have a complete solution. So we just keep these 2. And the form of the solution we are looking for Vs and P. Let's make it like a 2-dimensional vector, just for simplicity. We make it like a 2-dimensional vector just because they have the common multiplier, so why not to do this stuff? And this common multiplier is constituting sort of the singular part. So this is the, again, exponent and exponent of some function s capital, which is function of s, divided by e to the 1/3. Okay, in slightly different way it's shown here. Of course, it's exactly the same what I'm doing. So it should be breaking. You see that this is sort of the general multiplier, and it's necessary to stress that the small number here in denominator. So it provides very huge effect in change. When this small number and we reach some sort of the not central but a little bit remote part of the shear layer, we have very big number here. So it's of course constitutes this jumping nature of this shear layer. And so there is the sum of the up to infinity. So of course we have different power of 1/3 here. Better put n. We have n, which is the number of the corresponding contribution, and here we can identify z component like the n, and the pressure component because we found that e to the 1/3 of its contribution, and Pn. So this constitutes formula 3b2. Okay, somehow we a little bit finished, and as people asked me to get them to let them free just before, slightly before the 1 hour. Now it's 10 minutes remain to the 1 hour, so I think that we will have enough time. Yes? So we can stop at that moment, and you can proceed your laboratory work. Okay? So I just been asked that I should stop 10 minutes before 1 hour. Huh? Sorry? Question. So sorry, excuse me. Yeah, question, please. It's Z component. It's contribution to the Z component from which extract this star, and this star. It's just internal contribution, just to make clear how it is found. Sorry, I forget about questions. Thank you for questions. Что? Capital S. Yeah, this is maybe the most main function of all this stuff, because you see that it enter like in simpler part. So all the game is around this function. So it's the most important function, because it's here and in simpler form, like exponent, not simply exponent, but exponent is very high power. So this contribution is namely the single contribution which forms shear. So this is the most important function. We should speak many times about it, but at the moment I have many times. Okay, shall we finish?
This layer, what was it I showed?
Sir?
Boundary layer. Boundary layers, if I showed.
There is no boundary layer. Huh?
Boundary layers. The last class we have done.
Boundary layer.
Stevenson.
Stevenson, it's shear layer. It is shear. It's quite different. It's sort of the free layer, which is only due to that we have a big jump on the tangent cylinder. Because due to the geostrophic transformation or geostrophic flow to the spherical boundaries, we have huge jump. And this huge jump should be accommodated somehow by viscous force. And it constitutes the, I'll show. This picture shows that. You see that this shear layer, of course it has some boundary, but only not so big. Here and here on the top and here on the bottom. And there is rather complicated structure. At the moment we consider the most important one, which is inside, very inside, in the center, this one, e to the 1/3. Yeah, but there are another, a bit less important, but nevertheless they constitute the flow. So this is probably answered. No, around the sphere. Boundary condition is that there is an inner sphere and outer sphere, and the inner sphere is rotating slightly faster than outer sphere. And the boundary condition, of course, we put on the sphere. But here there is actually no boundary condition in the shear layer. In the shear layer, we should apply the condition that it's really just resolves the condition. So eventually, of course, there is some influence of the boundary layers on the shear layer, but it's not directly on the boundaries, on the extended boundaries of the shear. It's only on some intersection. This point, and this point, and this point. So it's not direct influence of the boundary layers on the shear. It is sort of indirect influence, just only very edge or very tiny edge. But the big influence is due to the fact that all the catastrophic rotation is inside tangential. Outside tangential is actually rigid rotation. So there is a huge jump in this. And to resolve it, we need this shear layer. Yeah, Maria found these two classical papers, and hopefully, Maria, did you upload it to the free access? These papers, please. Okay, so to the group that the students could read it. Yeah, please forward, and task as well. Okay, please share these papers as well. Okay, maybe it seems time for your lab or what? Yeah. Dystrophic what? Outside the cylinder, if we consider the situation outside the cylinder, at least in this approximation, when we have the differential rotation, given differential rotation, outside this, here the tangent cylinder, all this is tangent cylinder. Here there is complicated flow, but outside is just rigid rotation. Here and here is just rigid rotation. So it's quite interesting, and it's actually demonstrated in the magnetic field, because you know that all the main feature, aurora, inclination of the dipole, all appear, namely in these places. More precisely, of course, not exactly at these places, because here you have only the Earth's core. But if we extend this line up to the Earth's surface, then we exactly have the places where the aurora played the main role, where the magnetic dipole of the Earth inclined. So this tangent cylinder is perfectly working in the modeling of the planetary magnetic field and has experimental justification. Okay, please. Okay, we'll finish. Thank you very much for your question, especially.